welcome back to QBT. This week we are discussing state changes and internal energy. Okay, and there's no doubt that if you've been studying at school, you guys will have heard of the simple particle model, and how we can use that simple model to help explain the arrangements of particles in different states. And we know that we have three states of matter. We have solid, we have liquid, and we have gas. Well, there's plasma, but that's a different thing. If you go on to study physics a bit further, you'll learn all about physics and plasma and all of these wonderful things. But for your GCSE syllabus, there's solid, liquid, and gas. And when we talk about states, we talk about state changes, right? We can have a solid that melts into a liquid, and we can have a liquid that boils to produce a gas, right? We can have those state changes. And we also talk about internal energy when we talk about state changes. But instead of me just telling you what that is now, why don't you check out this tutorial which explains both of these things in a bit more detail.
Okay, so let's discuss state changes and internal energy in a bit more detail. Our prompt is to explain state changes in terms of internal energy. So I suppose the best way to explain this is to effectively draw three different states of matter, where we have a solid here, okay, we have a liquid, okay, particles are irregularly arranged but touching and flowing past each other, and then you have gas particles which are just pinging all over the place. Okay, so as we increase the temperature of a system, we can effectively increase its energy, okay, and in doing so we can change the state. So if we're going in this direction, we're increasing energy and we're going from solid, liquid to gas, and if we're going in this direction, we're decreasing energy, okay, and a way of doing that might be to decrease the temperature. Okay, and it's worth noting that state changes are physical changes rather than chemical changes, which means that the substance itself is not actually changing, it's just taking on a different form. Okay, so those are state changes. But how is this related to internal energy, right? That's a valid question. And I suppose to answer it, we have to first ask ourselves, what is internal energy, right? And internal energy effectively describes the total energy of a system, okay? So internal energy is equal to the particle's potential energy plus its kinetic energy, okay? Right? So that's the internal energy. If you were to heat up a system, right, you would be causing those particles to gain energy and move more. In other words, you would be increasing their kinetic energy. And in doing so, you would increase the internal energy of the system as well. So the reason that we say the particles move more, as I'm sure you know, is that EK is equal to half mv squared. Okay, so if we increase temperature, the particles move at a greater velocity, and if they move at a greater velocity and mass is staying constant, then kinetic energy has to increase. Okay, and if that increases, then internal energy must also increase. Okay, so we can talk about a system's internal energy and we can compare and contrast them. So we might say that the internal energy of a solid, right, this is say ice, okay, and then we give it energy and we heat it up and we melt it and we make water, okay, the internal energy, which is commonly denoted as the capital letter U, is going to be greater in the water because the particles have a greater total energy. And that's how we explain state changes in terms of internal energy.
Okay, hopefully that cleared things up for you. Hopefully you understand what state changes are and what internal energy is, how it's the sum of those two energies, the kinetic and the potential energy. If you want to learn more about physics, then please check out our other videos. We've got loads. And as always, please like and subscribe. It really helps the channel grow and helps us get more helpful physics content out to you guys. But in the meantime, stay quantum. Bye guys.